And let's look at the folder structure. Just like always, we're going to be in the Java folder, source, main, Java, FRC, and there's the robot folder. We're going to add another package to the robot folder. So remember, in Java, a package is a folder. So what you're going to do is make sure you've got robot highlighted, just like that. And then you'll click the folder button. And the name of this folder we're going to add is Subsystems. And a good rule of thumb when you're adding folders and adding files, no spaces. So in this case, the word subsystem is just one word. We don't need a space, so we don't have to worry about it.
Where are the laptops?
Which laptops?
MacBook.
So once you have the subsystems folder, you can add a subsystem to it. So the way we add a subsystem is you right-click on the subsystems folder, and then you should be able to scroll to the bottom, and there should be this create a new class command option. This will be the easiest way to add new files, and there's a whole bunch of options here. But we're adding a subsystem, so we're going to pick the one that's called subsystem. And we're going to give it a name. We're going to make a drive subsystem. Capital D for drive, capital S for subsystem. And when you press enter, once the name looks like that, it's going to make the file for you. All right, so we've got the subsystem. And there's a few things in here. So first off, we've got the package. What is this package telling us? And where do we find it?
You go to FRC, then robot, then subsystem.
Right, and that's hopefully where we put it because we put it in the subsystems folder.
Number one most important thing, the copyright.
We got the copyright, yep. Now we've got an import here. We're using this thing called subsystem base, and we can see that it extends subsystem base. What does it mean if it extends subsystem base? What was the analogy we used to describe that? I think before we saw it as our robot extends timed robot.
Oh, it's taking and using stuff from another file.
Yep, and the other file that it's taking stuff from is subsystem base. Okay, if we look down here, we've got this. What is this? So this is the class up here. We've got a word. We've got a set of open and closed parentheses. Not a variable. And we've got open and closing curly braces. What is something that looks like that called? It starts with an M. Method. And it's a special method because the name of the method is the same as the name of the class. What's that special method called? It starts with a C.
Class method.
Creative.
Create is closer.
Create method.
So if you've got a special method that's got the same name as the class, that is called a the constructor. What does the constructor do? The constructor constructs. So looking back here, this is the constructor for the drive subsystem.
Tells it what to become.
So it tells you how to make the drive subsystem. Okay, so this tells us how to construct the drive subsystem. Now, what's happening inside this method right now? Nothing. Now, does that mean the drive subsystem doesn't get constructed? No. It just means there's something special that happens. So let's think about making something special happen. We're going to look at a special kind of drivetrain called the Mecanum drive. Mecanum. Yeah, Mecanum.
I guess it tells you what this does. It says this method will be called when first scheduled.
Yeah, so the Mecanum drive has 4 wheels, and it has special wheels. It has those wheels that have rollers on them.
Oh yeah, I learned about those.
Can't they go like sideways or something?
Yep, it's a very simple drive for what's called strafing, being able to move side to
So
side.
the wheels want you to go
Yep, each wheel has its own vector for going off at a 45-degree angle, and depending on which way you spin the wheels, the vertical or horizontal components will cancel out.
One side going forward and one side going backwards, just like this.
Let's see, if you got one side going forward, those go back. That means these are going that way, these are going that way, these are going that way, and these are going that way. In that case, I think it won't move at all because I think it would perfectly cancel out. But that's the idea. So we're going to real briefly kind of do one of these mecanum drives. So I'm going to switch back over. And we're going to add some variables into the class. Now, in this case, we're going to use 4 motors. Why would we use 4 motors?
Because we can.
Because you have 4 wheels.
Because you have 4 wheels. And in mecanum, all of the wheels have to be independently controlled. So the way we're going to do this is we're going to start by doing it with PWM Talon FXs. So we're going to assume we're using basically Krakens for this. So if we switch back over, we're going to have 4 motors. And the way we're going to name them is they're the variables, so they'll be private. And here's another benefit we get from using the command-based robot is we can make them final. Final means once we make it, it's not going to change.
Can't change it now.
Right. So we got to give it a name. We got to give it a type. The type is PWM Talon FX. And now the naming comes in. So if we go back, here's the front of my robot. I've got 4 wheels. I need to give them names. It's a bad name. Those are bad names. Why are those bad names?
Because you don't know which wheel's which.
Don't know which wheel's which. I want to give the...
Front right, front left, back right, back left.
That sounds like a good way to do it. So we'll call this one front right, for example. And generally, back is an okay name. Generally, though, what you're going to find in the documentation are rear. So we use front and rear, left and right. So if we were to do this first one, we'll do front left, and then we'll add 1, 2, 3, we'll add 4 of them. Make sure we get front left, front right, rear left, and rear right.
Like copy and paste them all.
Yeah, it's all exactly the same except for different names.
Did you just control C then control V?
Yeah, Control C, Control V. So when you got all that, you'll notice a couple of things. One is these all have yellow lines under them, and it says this value is not used, which that's okay. Remember, the yellow lines are not problems; they're just potential problems.
Potential problem.
Now, drive subsystem is red. Now, if it's red here, that means it is a problem. And let's see why it's red. The blank final field front left may not have been initialized. So when you have all these things here labeled as final, it means, hey, I'm going to have something here, and it's not going to change. The problem is we haven't done anything here. Have we put anything in these variables? No, these are just empty variables right now.
They're useless to us right now.
Right. They will give us null pointer errors if we try to use them.
A piece of paper with no pencil.
A box with no toy, right? So here's a way we can use the constructor. We'll go into the curly braces, and we can start making front left. Now, how do we put something in the variable?
Parentheses.
Not parentheses,
Period.
not period.
I'm out of ideas.
Equals.
Oh.
And what goes in the front left variable?
The motor.
Which, well, not the motor controller, which is a
Talon FX.
PWM Talon FX. But it's not just a PWM Talon FX, it's a new PWM Talon FX. And it has to have a channel, we'll give it channel 0. And then I need to do the same thing for the other 3. So we'll do that. The only rule is they can't all have the same number. So we'll have to change their numbers. Now, if you had left them all as 0, it would not report that as an issue. It would not be a compile time error. It would be a runtime error. The code would crash as soon as you try to run it because
all motors can't be the same motor.
basically you'd be saying, I want to create the motor at port 0, and then I want to create the motor in port 0 again. And the hardware abstraction layer is going to be, hey, you can't do that. You already made this motor. But if you do this now, you'll notice the red for drive stuff went away. There's no more error there. But these are still yellow because it's saying, hey, the field is not used. And it kind of isn't, right? I put something in the variable. That's what happened on these 4 lines. But I'm not doing anything with them yet. So now what you can do, you could individually command these motors, but we're not going to do that. We're going to add another variable to the class. We're going to make our life a little bit easier. Private final, and we're going to create something called a mecanum drive. So WPILib has a lot of useful features in the library. One of the things it has is a mecanum drive. So we're going to make a mecanum drive just called drive. And so the nice thing with mecanum drive is if you give it 4 motors, it will do the calculations for you. And instead of having to control each motor individually, you can control just the drive. And so all we have to do is we have to go into the drive subsystem. Drive equals, it's a new what? New mecanum drive. And we just put in the motors. So the first motor it wants, if you read the documents, it says front left motor, so we'll give it front left. Then it wants the rear left. Then it wants the front right. And then it wants the rear right. And so that's the order it's expecting them in. And so what's nice here is, again, I don't have to touch front left, front right, rear right later. I can just work directly with drive. But there is one thing we didn't do. I'm going to switch over here. If you look at the way the motors would be mounted here, I'm going to draw the motors here in blue. This motor looks like that. This motor looks like that. Okay. So those are your 4 motors. The motors on this side all face left. The motors on this side all face right. So when you tell these motors to go forward, they will probably go forward. But when you tell these motors to go forward, they're going to go forward, but because they're flipped the other way, forward is going to be backwards. So one of the things we have to do if we're using the mecanum drive is we have to first invert the motors on one of the sides. And this largely depends on the motors. We're going to make an assumption right now. We're going to assume that when a motor spins forward, it's spinning counterclockwise. So that means when these motors on the right spin counterclockwise, they're going to be going basically in reverse. When these motors spin counterclockwise, they're going to be going forward. So the motors on the left are good. The motors on the right are backwards. So what we can do over here is we can say front right dot set inverted true, and we can say rear right dot set inverted true. And that's all we have to do. But one thing I like to do is if I do something to some of the motors, I like to try to do it to all of the motors. And what I mean by that is I'm going to set the front left and the rear left explicitly to false. And that way, when I come into the code later, I'm like, oh, hey, this is acting weird. I can see, okay, I'm setting all 4 motors to something. Maybe I need to swap what the 2 sets are. Again, this isn't something you have to do. This isn't even necessarily a better practice. This is just a habit that I've fallen into that has proven useful to me. And a lot of things when you get into programming, you're going to find, there's no hard and fast rule that says you have to do it this way. But sometimes there are things you're like, you know what? This actually makes my life easier if I do this. So what's interesting here is the drive subsystem currently still can't do anything, right? We've said, hey, drive subsystem, create your 4 motors. Hey, drive subsystem, invert the ones that should be inverted. Hey, drive subsystem, here's a drive object that will let you drive. But there's nothing in here that can actually tell it to drive. So what we're going to do is we're going to add another method. And we're going to add a method called public void drive. And we're just going to make it look like that. So a very, very simple method right now, but we're going to do some more stuff to it. First off, in driving a Mecanum drive, here's your robot again. There's actually 3 ways the robot can move. It can move forward and backwards. We generally call that the forward motion, right? Because backwards is just negative forward. It can move left and right, which we generally will call right motion because left is just negative right.
And then you have the X.
And then you have
The X.
rotation. So it can move forward and back, side to side, and it can rotate.
Can I move like this?
Isn't that just moving forward and right at the same time?
Yes.
So forward, right. So the nice thing is if I want the robot to move this way, that's really just moving this much right at the same time as moving this much forward. So by moving this way, I'm moving just a little bit right and a lot forward, whereas moving this way, I'm moving a lot right and a little forward.
It's void drive, right?
Yep, void drive, just like that. The idea is that you're breaking up motion into 2 dimensions. All of your left to right is independent of your up and down. And so by controlling how much of each one you do, you get that little bit more control. And these are both, here, are both called translation. This is called rotation.
Map all over again.
Yeah, if you think about a 2D plane, right? An object can translate in 2 directions, and it can rotate in a 3rd direction.
Your y-intercept and x-intercept can change.
Yeah, same idea. So we've got the forward, we've got the right, and so again, we'll want to call this the direction it is. That's counterclockwise. So sometimes you'll just see it called CCW, and we're just defining it that way. So if we go clockwise, would be CW. Yeah. So because of that, we're going to give our drive 3 inputs. We're going to give it a double forward, a double right, and a double CCW. Now the benefit of that, right, is I can now drive any way I want because those are the 3 pieces of data I need to know how to drive. And so by taking those all as inputs, I could maybe say, hey, drive 1 forward, 0 right, 0 rotation, and that will give me full forward speed. Or I could say, hey, drive -1 forward, 0 right, 0 counterclockwise. That'll give me full reverse speed. Or I could make those any numbers between 0 or -1 and +1, and I can get that range of motion.
This is more my territory.
Mm-hmm.
I use a lot of logicking in my game.
Right, it's the same idea. You gotta build some logic in.
Is this Python or Java?
This is Java. This is all Java. So now we go into the drive. So again, our drive though can't do anything yet. It's taking those inputs, it's not doing anything with them. But now we can make it do something. We're going to use that drive object, dot, and there's two ways you can control. There's drive Cartesian and drive polar. We're going to do drive Cartesian. And this is where we do want to do a little bit of checking. So if you write it out, it'll say drive.drive Cartesian, forward, right, CCW. This may not be correct though, and we're going to see why in a second. So when you're talking about how a robot drives, there are definitions of your coordinate planes. In WPILib, the robot is defined as being able to move along an x-axis. The x-axis is the forward axis. So we call that x.
That's a weird.
Yep. And positive is forward. We also have our y speed. Our y speed is measured in this plane, where positive is to the left.
That's so annoying. Why are the X and the Y swapped?
And then there's the robot's rotation rate around the z-axis, called z, and it's defined as positive for CCW. So what we want to check is forward is positive, counterclockwise is positive, but left is positive. So if we look back here,
Right is negative.
x, so the first argument is x, and x is supposed to be forward. And we said forward is positive, they're saying forward is positive, so that's okay. The next argument is the y speed. Now their y is left, but we've got right. So how do we fix that? We make it negative.
You do that?
Because left is just negative right. And right is just negative left. And for their third argument, z rotation, which they've said counterclockwise is positive, and we're giving it counterclockwise, so that's okay. So in this case, we've had to flip right, and that's the only one. One of the things you'll find as you're going through your code, there are a lot of opportunities for you to make things negative or not make things negative. And it's very important that you're clear with what's what. Because we were clear that this is a right speed, right is positive, it was easy to say, hey, they're expecting a left positive, I'm giving them a right positive, I just need to make it negative. So this is now a drive subsystem that has the ability to drive. The problem is it's not going to do that.
Because you can't control it.
Well, it's not that I can't control it. What is true about a class? What did we say a class is?
Blueprint.
It's a blueprint. We have defined the blueprint for a drive subsystem.
We have not built.
We have not built a drive subsystem.
You gave them the blueprint and they executed it.
Right.
Man.
And so one of the things you'll find, most of the code you write is going into the blueprint. And it's defining what it is, what it can do. Now we actually want to make a drive subsystem. We're going to go to the robot container. And all we're going to do is we're going to add one line below the command joystick, drive subsystem equals new drive subsystem. So one thing to notice here, the command joystick took an argument. It's got that 0 for the port. The drive subsystem, I'm not giving any parameters to. There's no parameters in here. But that's okay, because if I look at the constructor doesn't expect any parameters, so that's okay. So now I have created a subsystem. But I'm not doing anything with my subsystem. Right? We've said, hey, this is what goes into a subsystem. This is what a subsystem can do. And I've got a drive subsystem.